introduce the speaker that we have upcoming next here, Hari Subramoni. He's from the Ohio State University. He's going to talk about designing ROCm-aware MPI library for AMD GPUs over high-speed networks. So Hari is also no stranger to our OFA community. He's received his PhD in computer science from the Ohio State, and he is a research scientist in the Department of Computer Science and Engineering at Ohio State. His current research includes high-performance interconnects and protocols, parallel computer architecture, network-based computing, exascale computing, network topology-aware computing, QoS, and it goes on. And we have heard few of those discussions the past few years. He has already presented over 70 papers in international journals and conferences related to these research areas that he participates in. Recently, Dr. Subramoni is doing research and working on design and development of MVA, MPIC, and other software packages. He's a member of IEEE. So Hari, please welcome, and I'll give the stage to you now.
Thank you, Divya, for the kind introduction. So, hello, guys. As usual, I'd like this to be a dialogue, not a monologue. I'm sure that all of us here can talk about the stuff that they're doing for hours on end. So let's try to make this as interactive as possible. So I'm here to present a work done in our group together with colleagues Carter, Jahanzeb, King, and of course Dr. Panda. So the topic is going to be how can we design a ROCm-aware MPI library for AMD GPUs over high-speed networks. Now, all of you guys are aware that there are lots of GPUs coming up in the ecosystem right now. So NVIDIA GPUs has been dominating the GPU ecosystem for a long time. Now, recently, AMD has introduced their GPUs, the MI25, MI50, MI100 range of GPUs. Similarly, if you look at Intel, they're also coming up with GPUs from their end through the OneAPI, SYCL ecosystem. In this presentation, we're going to share our experiences in designing a ROCm-aware MPI library, which takes advantage of many of the features that the ROCm software stack from AMD provides us, and see how we can extract that up to the application level so that the end applications see the benefits. As our keynote speaker very correctly mentioned, software, software, software. So without the right set of softwares to take advantage of modern hardware, you can't really expose the kind of benefits to the application level. This is a brief overview or outline of how the talk is going to proceed. We'll obviously introduce the problem, try to highlight some of the GPU-aware communication features that we are going to use in designing a ROCm-aware MPI. We'll have some slides showing the performance of the said ROCm-aware MPI library. And finally, we'll conclude with some remarks about future work. As we all know, GPU-aware MPI libraries as well as other GPU-aware communication libraries have been the driving force behind scaling of applications, both the HPC as well as deep learning on GPU-enabled HPC and cloud systems. So far, this has been dominated by NVIDIA GPUs and the CUDA software stack. Recently, as I mentioned, a lot of other organizations have begun introducing their own high-performance GPUs into the ecosystem. But unfortunately, lack of support for high-performance communication stacks with the newer AMD GPUs limited the adoption of the said GPUs in large-scale HPC deployments. So for instance, if you look at the upcoming DOE exascale systems like Frontier and El Capitan, these would be driven by the AMD GPUs. To take advantage of the AMD GPUs, just like the CUDA software stack, AMD introduced their Radeon Open Compute platform. So with this as a background, there is a need for a Radeon Open Compute platform aware MPI library so that users can exploit the capabilities of AMD GPUs on such emerging exascale class systems. So to that end, we design a ROCm-aware MPI where we integrate the ROCm runtime into GPU-aware MPI libraries like MWAPH2 GDR to utilize the high-performance AMD GPUs which are coming into the ecosystem. So what are the different GPUs that we have played around with so far? So these are some of the GPUs in the AMD MI series. So you have the MI25 Vega GPU architecture. You have the MI50. Again, this is like a higher end version of the MI25 with more memory as well as slightly higher performance per flops. You have the MI100s, which are probably going to be on the next generation systems, which offer much higher performance uh, uh, compared to the current MI50 architectures. So what exactly are the newer features that we are going to use here? Now, before we go there, what is GPU-aware MPI library? So what's the big deal? So if you typically look at it, how is the modus operandi for using an accelerator? So what you would typically do is you have some data on the host, you would move it to the accelerator, perform some compute there, move the data back to the host, and then send or receive it. Now, this is how things have been so far. But can we enhance this? Can we optimize this? So this kind of operation, while is okay, does not lead to the best productivity for the application developer who has to stage a lot of data and do a lot more operations. So can we do it in a optimized fashion so that all the application developer has to do is a send and a receive? This could be an MPI send or whatever. But can the application developer just do a send and receive and have the communication runtime do the optimal processing to move the data from GPU on one node to a remote GPU on another node? Now, in theory, this is very simple. So what is the big deal? The big deal is this. In order to achieve this, one can have almost 16 different communication paths depending on available technologies, depending on hardware topologies, relative location of the GPU and the network adapter, and things like that. So this is where the complexity comes in. If you bundle this complexity or if you move this complexity to an application developer, they would just get lost. The application developer or the domain scientist should be just focused on developing their domain science, not figuring out, okay, if a GPU is on one socket and if the network adapter is on the same socket, and is it connected by a PCI switch or is it going across like a PCI switching domain, things like that. So a domain scientist should not be bundled with these overheads. So this is where a GPU-aware MPI library comes in, which provides high performance and high productivity for application developers and domain scientists to get the best application level performance on emerging GPU-powered systems. So these are like a highlight of some of the communication features that typical GPU-aware communication libraries utilize to get that high performance. So let me first start with the NVIDIA / CUDA side. So there, typical libraries were using NVIDIA's GPU Direct RDMA features, which they developed in conjunction with Mellanox, which is now NVIDIA. They used CUDA's interprocess communication or IPC features, as well as what is called as GDR copy, which exposes some portion of the bar 1 memory on the GPU to be accessible from the CPU side. Now, if you go to the AMD GPUs, they have equivalent of these technologies there as well. So instead of GPU Direct, they have what is called as ROCm RDMA or Peer Direct. They have the CUDA's IPC equivalent of ROCm IPC. They also have what is called as a large bar feature, where the host can directly access certain memory regions on the GPU side without the necessity for any kernel modules like GDR copy. So these are the three major features that we are going to be using to design a high performance GPU aware MPI library. Now, having mentioned this, let me go into the ROCm aware MPI design. So before that, what is a ROCm? AMD developed ROCm, or the Radeon Open Compute Platform, to be tailored towards achieving efficient computation and communication performance for application running on AMD GPUs. So this is obviously available in an open source fashion for AMD GPUs from the following GitHub. So here we design and demonstrate early performance results of a ROCm-aware MPI library that uses this high performance communication features like ROCm RDMA, the ROCm IPC features, as well as the large bar memory feature to achieve scalable multi-GPU performance on modern HPC systems. So to this end, the first thing that we do is identify all the underlying communication primitives that an MPI library or an MPI runtime offers, and trying to see if we can abstract out this information so that we create a scalable, portable MPI library which can be easily extended to different classes of GPUs. Let's say if you want to use the CUDA APIs with NVIDIA GPUs, or ROCm APIs with AMD GPUs, or the um, Intel SYCL 1 API framework with the upcoming Intel GPUs, we should be able to do that in a seamless fashion in MRAPID2 GDR. So this is the kind of framework that we are going for, where you have an abstraction interface inside the MPI runtime which can easily let's say switch between different underlying communication APIs as well as hardware. So let me give a brief overview of the MRAPID project. So we have been in the community supporting high performance computing for the last 20 years. We have been used in a lot of HPC systems around the world. So as part of this work, we have done the following things inside MRAPID2 project. So we have added support for the AMD GPUs inside MRAPID2 GDR. The set support has been released a few months ago and is available with the MRAPID2 GDR 235 release. In line with our typical development methodology, whenever we release a new feature, we also have some support inside the OSU microbenchmarks to measure the performance of basic communication operations. So the OSU microbenchmarks version 5.7 has support to measure the performance, basically communication performance on the AMD GPU platform. And this is also released like a couple of months ago. So if you guys want to actually try out any of the things that is being presented as part of this work, you can download these software stacks from the MRAPID website and try it out for yourself. In fact, we do encourage you to do that and give us any feedback that you may have. So let me just go forward to the performance of the ROCm-aware MPI now. So this is a detail. These are details of the different software stacks used for performance comparison. We use the MRAPID2 GDR released version, which has the above said support. The GPUs used for point-to-point operations were the AMD MI50 and MI60 GPUs, and we also used the OSU microbenchmarks version 5.7 with support for performing data transfers from AMD GPU devices in place. So this is a detail of the experimental setup. We used the Corona cluster at the Lawrence Livermore National Labs, which has about 291 AMD EPYC series CPU nodes. Out of this, 82 nodes have MI50 GPUs, 82 nodes have MI60 GPUs, four each, and an additional 123 nodes have 8 MI50 GPUs per node. Each node has a dual like it has two sockets, and it has a Mellanox IB HDR adapter. The Mellanox OFIT version was 5.0 and the ROCm version was 3.1.0, and these like continually change as newer versions are coming up. We used the publicly available MRAPID2 GDR235 software stack, and we used an OpenMPI 401 plus UCX 190 for performance comparisons against our proposed work. So let me start with your basic intranode communication performance between MRAPID2 GDR with support for the AMD GPUs and OpenMPI with UCX. So here we have intranode latency and bandwidth shown. So as we can see, MRAPID2 GDR's intranode latency for 1 byte using the PCI bar mapped memory feature is close to 1.78 microseconds device to device. So this is actually very, very, very low number for intranode development. Again, as you message has increases slowly from 1 byte to 4K bytes. Joe, if you don't mind, can you share like start from slide 16? I think my computer is refusing to work with me today.
Will do. One second.
Thank you kindly. Apologize for the hiccup.
In the meantime, Hari, there is a question that came to you.
Sure.
Why does bandwidth decline at the 4-meter message size? I think is a question. Is there a bandwidth and the message correlation that you can talk about?
So for 4 megabytes?
Yes.
Yeah. So this is probably due to some like cache effects that we are seeing. So we are still trying to understand what exactly is happening after 2 megabytes and trying to figure out why the bandwidth is dropping. So hopefully we'll have an answer for that shortly. Thank you, Divya. I appreciate it. Before I proceed, any other questions?
Yeah, we have about 75 attendees. Please feel free
Okay.
to ask your question and should be able to open your mic.
Okay, that should be fine. So feel free to ask any questions that you have, guys. So now let's go to the internode performance that Joe has kindly shared for us. So here we are measuring the performance of MAPIS2 GDR and comparing performance against OpenMPI with UCX for basic internode latency and bandwidth. So this is across 2 nodes. So here again, for the latency, we can see that the MAPIS2 GDR and OpenMPI are kind of similar. Both of them uses the ROCm peer direct feature. However, if you look at the bandwidth performance, MAPIS2 GDR is able to achieve an internode bandwidth of close to 12 Gbps at around 512 kilobytes, and that kind of remains all the way through up to 4 megabytes. So here we are able to significantly outperform OpenMPI plus UCX. The bidirectional bandwidth, again, for the small to medium message sizes, MAPIS2 is much better than OpenMPA, but as we get closer to the large message spectrum, the performance becomes similar for both libraries. Next slide, please. Oh, okay, so that was the point-to-point performance. Now we are looking at the collective performance here with different collective operations like broadcast and reduce. So as you guys know, collectives are kind of built on top of the point-to-point performance. So the benefits that the MAPIS2 library has built up at the point-to-point level kind of reflects at the collective level as well. The second aspect that happens inside collectives is the performance of the individual collective algorithms themselves. So inside MAPIS2 GDR, we have a lot of tuning and optimizations to select the right collective algorithm at the right message size. So the benefits that we are seeing here are like the result of both having more optimal basic point-to-point communication mechanisms as well as having more optimal collective algorithm selection. So with these two, MAPIS2 GDR is able to get a broadcast latency of around 7 microseconds at 4 bytes and 3 milliseconds at about 4 megabytes, which is significantly better than OpenMPI plus GDR, and similar trends holds for reduce as well. Next slide, please. So here we look at the performance of gather and all gather, and the trends are kind of similar as we saw earlier with MAPIS2 GDR through a combination of both enhanced lower level like point-to-point performance and collective optimizations, being able to significantly outperform OpenMPI. Next slide, please. So here we look at the more critical collective operations like all reduce and all to all. So here we were able to like with all reduce at least we were able to significantly outperform OpenMPI for all message sizes. For all to all, Unfortunately, there was a node failure with all-to-all when using OpenMPI for large message sizes. So that's why the graph on the right bottom only has numbers for MVAP2 GDR. So we are trying to see if by upgrading to a newer version of OpenMPI, we can kind of circumvent this issue. Next slide, please. So with this, we kind of come to the end of the talk, and we'll conclude the talk here. Next slide, please. So in this work, we presented the design of a ROCm-aware MPI library in MVAP2 GDR, which is capable of exploiting the AMD GPUs. We utilize some of the communication features offered by the ROCm driver and the runtime to integrate this support inside GDR. So specifically the features that we use is ROCm RDMA, ROCm IPC, and the large bar feature. We optimize the communication performance on AMD GPUs for point-to-point and collective MPI operations, and demonstrate the scalability and performance of the GDR ROCm-aware feature. So some of the future work that we want to do is to see if this GDR ROCm-aware support can perform well with HIPified applications, and what sort of benefits that we get at the application level. So I saw a question there. Just to note, this is even though it is like MVAP2, sorry, even though I mentioned it is a Mellanox HDR card, it is HDR 100, not HDR 200, which means that the line rate is still 100 Gbps. So I also saw another question in chat from Jamin. So Mark, I hope that answered your question. So Jamin has a question. Do you have any insights on why MVAP performs worse than OpenMPI plus UCX in the bandwidth range less than 64 kilobytes? So in order to get better point-to-point performance, we have to use a combination of multiple features for different message ranges, which includes the usage of the large bar feature, using loopback-based transfers for like the medium message ranges, and similar operations at the receiver side. Without a combination of these three being used for the right message sizes, we will not get the best performance. So our guess is that OpenMPI plus UCX does not have like that level of tuning for all the message sizes, and that's why we are seeing the degradation. So Jamin, I hope that answers your question. So with that, I'd like to conclude this talk. And if you have any other questions, thoughts, comments, I'm more than happy to address them.
Yeah, we can take a couple of questions here. We have time for it. So anyone have any questions for Hari?
So let me quickly check with Mark and Jamin. Did I answer your questions? Or if you have any other thoughts, please feel free to chime in.
Yeah, thank you for the answer. Like I said, didn't quite understand your answer. So I guess you were saying that MVAP does a lot more tuning than OpenMPI with the various message sizes?
Yes. So, so basically with the point-to-point operations, if you look at it, for very small message sizes, you need to use the large bar feature. But once you go past a particular message size, the large bar is no longer applicable because of memory limitations. So at that point, we need to think of a different mechanism to move the data. So that is where we try to perform kind of a performance trade-off analysis between using a loopback-based data transfer, as in using the network adapter to like stage the data from the AMD GPU to the host and then perform internode transfer, versus using like a memcopy kind of operation. So unless you kind of know when exactly to switch from one feature to the other, you might not get the best kind of performance. So like that tuning is what is missing in OpenMPI.
Oh, okay, I see. Thank you.
Okay, good to know that that answered your question, Mark. Any other questions, thoughts, or comments? Okay, if not,
Okay.
thank you. Thank you, Divya.
Thank you, Hari.